Now in this section we're going to take a look at something called the matrix equation. Now first and foremost, a matrix equation is just an equation that involves matrices. But it's more specific than that. A matrix equation is something that's associated with every linear system. But before we can really pin down what the matrix equation of a linear system is, we need to understand a new operation between matrices. In particular, we need to talk about matrix multiplication. Now we're going to start by introducing matrix multiplication in a very narrow context, and then later on it'll be generalized. But for now, we're going to start with a very specific setting. So let me just give you a quick reminder first. If you have a matrix, you can always partition it into columns and write it as just a single row of columns. So if I have an m by n matrix, then I can just write it as a single row, A1, A2, all the way up to AN, where each of these A's actually represent the columns of the original matrix A. Okay, so if with that in mind, we can get to the following definition where we actually talk about a product. So let's take a look here. So here's the situation. You've got an m by n matrix A, and you've got it written in the manner that I just said, right? So you've written out the matrix A in terms of its columns. So it's written as a row of columns where A1, A2, all the way up to AN. Those are just the columns of the matrix A. Okay, and you've also got another matrix, which happens to be a column vector in Rn. So it's an n by 1 matrix consisting of a single column, which in practice this will be generally it'll be a vector, but it's still a matrix. So in this case, you can define the product of these two objects in a very specific way. So this is how we do it. We define the product of A and X. It's given by this rule here. Okay, so let's take a closer look at this. What's going on? So AX, let's just start with this, the simple part. AX, that's just the notation that you use to write down the product. Just says I'm going to multiply the matrix A by the column vector X. Okay, so then what's coming up next? Well, this is just the same thing, right? This is the exact same thing written down, except instead of just using the symbol capital A, we've replaced A with its definition as a row of the columns A1, A2 up to AN, and then the vector X has been replaced with its definition as a column matrix. So here's your A, and here's your X. So nothing really has changed. This step here is not where the definition actually takes place. This is just giving you two different ways to write the product, but it's here where the actual definition can be found. So how do you actually compute this product? Well, it looks like we take column 1 from the matrix A and we multiply it by the first coordinate of the vector X, and that's what gives you this here. It's a scalar product. So A1 is a column vector and X1 is the first coordinate of the column vector X. Then you're going to take column A2 from the matrix A and you're going to multiply it by the second coordinate of X, and that's what gives you this scalar product here. And you do this one by one until you get through all the columns of A and all the coordinates of the vector X. Notice that the final index for the columns of A, the final index is n, because n is the number of columns. That's guaranteed by this assumption up here, right? We started with the assumption that A was an m by n matrix. That means there's n columns. And also we had as an assumption that X is an n-dimensional vector, which means its final coordinate is going to be its nth coordinate. That's what I mean when that's what I meant when I said we're going to define matrix multiplication in a very narrow context. There's a lot of assumptions that have to be satisfied before we can make sense of this. But in that case, this is how you multiply a matrix A by a vector X. And anyways, you keep on going till the very last product where you have xn multiplied by an. So that's you're taking the last coordinate of the vector X and you're multiplying it as a scalar onto the column vector an. Okay, so that's the formal definition. Let's look at a couple of examples. So here we have a 2 by 3 matrix A, and we're multiplying it by a 3 by 1 vector X. So we're just going to follow this rule essentially here. So we're going to pick off the first coordinate of this vector here. So we'll have 3, and then we'll multiply it by the first column of this matrix. Why don't we give this a name? Let's call, just for the moment, you don't even write this down. I'm just going to do this for the moment just so I can refer to it out loud so you know what I'm talking about. Okay, so we took the first coordinate of X and we multiplied it by the first column of A, and that's what got us here. Okay, that's our first term. The next term is going to be the second coordinate of X multiplied by the second column of A. So we'll have plus negative 5 times the vector 7, 0. I'm just going to go minus 5 times 7, 0. That's the same thing. And then the last product we'll have is we'll go plus 2. That's the last coordinate of x. And we'll multiply it by the last column of A. Okay, so that's the definition. But now, since we actually have numbers here, we don't need to stop. We can actually completely simplify this down until it's a single vector. So let's multiply the 3 into the first vector. Let's perform this scalar multiplication. So you're going to get 3, 9. Then we'll perform this scalar multiplication. So it'll be minus 35, 0. And then we'll perform this scalar multiplication. So we'll have plus negative 4, 8. And then now we can actually perform this last bit of arithmetic and figure out what the result will be. So we're going to take the vector 3, 9 and then subtract the vector 35, 0, and then we're going to add the vector negative 4, 8. So we can just do it like this. 3 minus 35, that's going to be negative 32. Then you add negative 4, you're going to get negative 36 for the first coordinate. Then for the second coordinate, you're going to have 9 minus 0, which is 9, plus 8 is 17. Okay, so that's our final computation here. So let's put a box around this. And let's reflect a bit on how this went. I'm going to erase this because I want to add another annotation there. Notice that this matrix was 2 by 3, and that this matrix, it's a vector, it's a column vector, but it's still a matrix and it has dimensions, was a 3 by 1 matrix. And then this matrix here, again, it is a vector. It's a column vector, a two-dimensional column vector, but it's also a matrix with dimensions 2 by 1. So here's what has to be true. Okay, you can think about, you can read the assumptions up here carefully, or you can just think about it this way. These two numbers must match up. Let me just draw a ring around both of them there. Those two numbers must match up for this process to work. You need to make sure that you have the same number of columns in this matrix as you have entries in this vector. So that amounts to checking that these two numbers agree. And they do, so that's why this worked. Then the two outer numbers, the 2 and the 1, that gives you the dimensions of the product. That's worth remembering. In general, we have this. Let me add the general situation. So A is m by n, and x is n by 1. Okay, and the result, it's written as a linear combination, so you can't, it maybe seems weird to call it a matrix and say it has dimensions, but it does, because A1, A2, all the way up to AN, those are all m by 1 matrices because they're vectors in Rm. So once you put them together as a linear combination like we did here, right, we actually did the arithmetic and actually collapsed them into a single vector. You're going to get a matrix here, which is going to be of dimensions m by 1. So that's worth remembering. Okay, so let's take a look at the next example. So we've got a 3 by 2 matrix and a 2 by 1 matrix that we're multiplying. So we're going to have, if we follow the same rule, we're going to have 2 times the first column, 0, negative 6, and 1. Then plus 4 times the second column, which is 4, 3, negative 2. Okay, so then after this, it's just simplification. So we'll multiply the 2 and the 4 in, and we'll get 0, negative 12, 2, 16, 12, negative 8. And then when you actually put these together, you're going to get 16, 0, and negative 6. So that is how we can multiply vectors by matrices.